Hey guys, my name is Pete.
What's up? My name is Wallace.
Alright, today we're going to be talking about the ideal gas law, so get ready. It's pretty awesome. Alright.
Yeah, that's right. So here we've got a couple properties of gases. P, which is the pressure of the gas. V is the volume of the gas. N is the amount of gas. And T is the temperature, measured in kelvins. Remember that.
Yeah, oh, well, it can be in anything, but usually we'll want to convert to Kelvin. So we have Charles' law, Boyle's law, Avogadro's hypothesis. We talk about all of these three in different podcasts, but essentially what we need to know here is that in Charles' law, volume and temperature are proportional, directly proportional. In Boyle's law, pressure and volume are inversely proportional. And Avogadro's hypothesis states that the number of moles of gas, or the amount of gas, is proportional to the volume. All right. So we combine these laws, and what do we get, Wallace?
We get the ideal gas law.
Right.
PV equals nRT. Probably the most important thing you need to know about gases. Pressure times volume equals the moles times R times the temperature.
Right.
Now, what is R?
R is the ideal gas constant, and we have some values of R depending on what units you're using. So we have like atmospheres, and sometimes we will be using joules, meters cubed, torrs, whatever. Essentially, these are, you have to make sure you have your units correlate with one of these values. All right. All right, guys. So we can replace N. So again, the amount of gas with mass over mole mass, and we also have our formula for density, mass over volume, which is equal to m over v. And so if we replace N with m over m, where lowercase m is the mass and uppercase m is the molar mass, we get this equation at the top. And if we introduce density to the equation, we get that density equals Pm over RT, right? So the pressure times the molar mass over the gas constant times temperature. All right, so now we have a problem, and Wallace will go through this problem.
That's right. So we have the problem 25 moles of gas are heated to 50 degrees Celsius in a container with a volume of 35 liters. What is the pressure of the gas?
We have our equation, PV equals nRT, right? We want to write down everything we know. So the unknown, what we're looking for is pressure. We have a volume of 35 liters, 25 moles of gas, and we are going to be using the gas constant at 0.0821, which correlates with our units, and we have 323 Kelvin. Now, if you're wondering where we got 323 Kelvin, we are given that it's 50 degrees Celsius, and to convert to Kelvin, we'll add 273. All right.
Right, so we have our base equation, we plug in the values, P equals that fraction over there, we just brought P to one side, we solve for P is 18 atmospheres of pressure.
Now we have another problem. So if 0.900 grams of an unidentified gas occupies a volume of half a liter at 101 degrees Celsius at a pressure of 0.970 atmospheres, what is the molar mass? All right.
All right, so we use the equation from before, PV equals nRT. We have 0.97 atmospheres for our pressure, half a liter for our volume. We don't know the moles. We're trying to find out the moles for this equation. We have our ideal gas constant, 0.0821 atmosphere liters per moles Kelvin. We've got our temperature, 374 Kelvin. We got that by adding 273 to our Celsius number, which is 101 degrees.
Right. Nice one, Wallace.
Thanks, Pete.
Okay, so basically we've rearranged the equation so that n is on one side, and then we just go through the calculations, and we get that n equals 0.0158 moles. But we're not done here. Why are we not done here, Wallace?
Well, that's not what the problem's asking for. The problem's asking for the molar mass. We only have the moles.
Right.
Well, thankfully, in the problem, we got the mass. We know for a fact that moles is the mass over the molar mass. From that, we can find out that the molar mass is equal to mass over moles. Well, why is that useful? Well, we have the mass, we have the moles, we divide them, we get the answer. 56.96 grams per mole.
Right.
Problem solved.
Nice. So, all right, we have another problem, a little more interesting problem here. So we have one is the density of 1 mole of O2 gas at 1 atmosphere and 273.15 Kelvin. This is also a standard temperature and pressure.
All right, so we know for a fact that density equals Pm over RT. Remember, we derived this previously in the podcast. Now we just plug in the numbers. 1 times 32, which is the molar mass of oxygen. If you want to know how we found that out, go to our molar mass podcast.
Right. To clarify, Wallace, we looked at the molar mass of oxygen 16 on our periodic table, and then we multiply by 2 because it is diatomic. That's a key part. All right. What do we get, Wallace?
We get 1.43 grams per liter. That's an accurate measure of density. We got the answer.
Nice. All right. So that is the end of our presentation, guys. So thank you guys for watching. We hope you enjoyed these podcasts. We will be posting more podcasts with related topics to the one you just watched right now. And the more we know,